Applause for being in person, I guess. Yeah, Jason Stenson, research assistant in the Energy Studies and Buildings Lab, Institute for Health and the Built Environment at the University of Oregon. And I have 3 ongoing projects to discuss today. The first is mycelium, developing a biocomposite acoustic mat alternative for mass timber assemblies. And the driver for this really comes from some of our acoustic testing and research that we've done, field testing images on the top, and lab testing, ASTM lab testing that we've helped facilitate since the inception of TallWood Design Institute. In all of that research, we've looked to industry partners for what's missing, what needs to be tested still, and what are market drivers for assemblies involving mass timber construction. Through that, we've heard a need for more bio-based materials, and we've also, through previous ARS funding, designed and built this microacoustic test chamber. So it takes a 32 by 32 inch floor ceiling test sample. It uses the space that it's in as the source room and has an inner chamber as the receiving room. The caveat is that we can't test down to low frequency thresholds required for ASTM testing, but it's great for quick and iterative comparative testing, and we're using that in this current research. So mass timber buildings are made of wood. Wood is resonant. Stringed instruments have a piece of wood connecting the top of the instrument to the back usually, and it's called a sound post. There's many of them in mass timber buildings. We just call them columns. The acoustic treatment is needed for most use cases, and many of those materials have high embodied carbon, are made from petroleum-based products, or potentially have health impacts for those installing them. Renewable bio-based materials are not new. They have some added benefits towards their end of life in a building scenario, that they can be recycled through composting. And some examples here, left to right across the top: thatch, straw, earth, bamboo, cork, wood, of course, hemp, and mycelium in the lower right. What is mycelium? It's the root-like structure that makes up about 90% of the organism, and the mushroom, in this case, is the fruiting body of that, but most of the organism is mycelium. So our interest here is in acoustic panel development, and there has been research in thermal insulation products, and we're drawing on some of that, but using it as a inner layer in a floor ceiling assembly for a mass timber floor assembly. So here's the recipe development and process. You need a substrate. It is a composite that needs to be sterilized. You inoculate with a fungal spawn or spore. Once that sterilization substrate is cooled, and that's mixed and filled into formwork and covered to retain moisture for the growing period, which can be in the order of 2 weeks, depending on 2 to 3 weeks, depending on the mix. That's then dehydrated. In our case, we're bringing it down to a moisture content of 5%, however long that takes, typically a couple of days. And then we're testing that for acoustic properties, and also we'll be testing it for material properties, physical characteristics. So here's some reishi spore being ready to inoculate the substrate. 2 different sequences of growth over time, left to right. You can see some mushrooms breaking through the plastic wrap on top as it grows. 3 different samples. We have a number of different substrates, 2 different spore species, oyster and reishi. And a big part of this project is really just developing that that growth and recipe, I'm going to call it, for the sake of making an acoustic panel that can be handled and transported and installed and have high quality properties. So that first one, we've already found that this wood wool is a great substrate for mycelium growth, has lots of voids and also retains some of its physical properties. Here's some more wood wool partway through its growth phase. And this one is sawdust. It makes a much denser mycelium panel, but it's a brittle panel because there's not as much holding it together with the smaller fibers. Here's some images of dehydration. Just using a food dehydrator. So to get to our 32 by 32 acoustic samples, we're combining 4 16 by 16s based on this dehydration size that we're at. So some time lapse of our acoustic testing. This is the microacoustic test chamber. There's a microphone in that box. This is 5 lam CLT as our base panel. Mycelium panels as an inner layer, and a 3-inch concrete topping slab. And the secret sauce to the microacoustic chamber is the sand. That's our primary sound insulator. It's great because it's massive like concrete, but it has lots of interstitial air spaces that stop and delay sound transmission. There's a putty being placed to stop additional sound transmission, and a tapper used for impact testing, and a microphone placed on top when we're doing the airborne sound transmission. The sound source is a speaker that's mounted on the ceiling, an omnidirectional speaker. So scooping sand is kind of our version of paint drying, so I've edited out much of that. But what I would point out is that as the mycelium samples go on and off, there's quite a variation in color, in densities. There's some broken ones that didn't stand the test of getting up to Portland and placed on the in the test sample, and also some that shrunk out of the formwork as well. So our acoustic testing is complete, and we're ready to start some of that material property characterization. We've got 10 different recipes of mycelium sample that is kind of our second round. We did at a smaller scale, many more, tens of samples more with different recipes. And these were the 10 that we produced at this scale for acoustic testing. And again, a sequence through the acoustic testing process at the end there. So preliminary results, not meant to be read, but there's our 10 samples in the solid blue bars. And our reference sample also tested in our acoustic chamber with just the CLT and 3-inch concrete topping slab. These are impact results from the tapper, so better performance over our baseline, but also good variation across our 10 different test samples. And here with airborne results, again, improvement over baseline and variation across those. So looking to those material tests next as the next steps for determining viability for producing at a larger scale and fine-tuning a particular mycelium acoustic panel. This is from the last year's Venice Biennale, the Belgian pavilion, and I'll leave you with that mycelium inspiration as we go to the next project, infiltration of all wood facade construction techniques. Mark Fretz is the lead PI of this project and the previous one. The background here is some field studies we did at Waechter's Mississippi building in Portland. We did a number of studies, acoustics, air quality, and others, but looked at infiltration as well. It's a wood, CLT facade with a half lap as the construction. And one of the things we attempted to do was to isolate that facade to look at infiltration just through the wall assembly, using a blower door setup and thermal imaging, and taping off as much as we could those real world, real building penetrations. And one thing we found, in addition to thermal imaging of the wall-to-wall panel joints themselves in variation across half lap and corner butt joints, was this under depressurization, even with that floor-to-wall joint taped, we're seeing warmer air from the coffee shop below being brought up through the natural checking and splitting the cracks in the first lamella of CLT as additional, in this case, transmission within the building, but an additional air path that made us, for the current research, devise a more controlled laboratory experiment around these test variables. The first being comparing 3-lam CLT spruce pine fir from Klishnikov to 4-inch mass plywood. 3 different joint types: the half lap that we saw at Waechter's building, a exterior plywood spline, and a cross screwed butt joint. And then treating that joint in 4 different ways: just fasteners, adding a weather barrier over that, adding just sealant in the joint and fasteners, or everything together. So those 24 iterations are what we're right now going through data collection for. This is what we think a mass timber infiltration test chamber looks like. It's an 8 by 8 foot wall area, which is coming from some ASTM envelope testing standards, but we've increased the number of wall joints because that's really what we're looking to study. And so we've got 7 very skinny wall panels and 6 wall-to-wall joints to sort of amplify that leakage through the joint and minimize any noise from our test setup. And we're doing some tests both with visible smoke at low pressure to see where that leakage is happening, and more importantly, to confirm that we've sealed the perimeter of the test wall to the chamber. We're using a duct blaster system, which is typically used for HVAC testing and analysis to pressurize and depressurize the chamber at 16 different levels up to 400 pascals. So more fun time lapse here. This is, we had a reference test panel that was reused CLT spoil board. And we coated that with the same elastomeric paint that our chamber is coated in, as well as some silicone at the joints. This is us installing the 4-inch MPP half lap. We're making sure the joints are tight and fastening each as we go. That way that we're not compressing those joints more than they would be in a building installation when we compress the test wall assembly into the chamber here, using unistrut and all thread in 2 directions and bar clamps in the 3rd direction with a movable frame on 2 of the 4 sides. So that's our first iteration, fasteners only. Now we're putting on, well, Phil and Dale are putting on a weather barrier, Suprema peel and stick here, taking off just as many pieces of all thread as we need to get in there and rolling that on so it has good adhesion to the mass timber, and again reassembling and confirming that the chamber is sealed and going through the test. That's not in the imaging here. So now we've taken the screws out, separated the panels apart, and are putting in sealant, a bead of sealant down the joint. This is Henry's 925. Again, we're getting our products based on industry feedback and reaching out and using that as a resource to do applicable research. So the weather barrier has remained between the joints. One reason is we're focusing just on the joints, but we're also, it's quite sticky. So if you tried to pull it all off, if you get it off, you're going to take a lot of fiber with it. So this is our 3rd test looking at fasteners plus joint sealing. And we're doing each of these tests for each of those wall types and joint types. So this fourth set is reapplying and overlapping weather barrier, rolling that on as well. So this test is set up, and we're partway through in Emerson, and conveniently, because we're doing it in Emerson, we had originally planned to do this in our Portland lab, but since we're in Emerson, we can call a crane operator over, and that test panel can go somewhere else for the next test. So we're still collecting data. We haven't processed any of it, but I've cherry-picked a couple of numbers here for you. The two series that we have done are the CLT half-lap and the MPP half-lap. A standard commercial metric is CFM 75. That's a whole building metric for your building envelope at 75 pascals. We probably will be reporting this more in per lineal foot of joint and crack area, which is more applicable to comparing them down the road. But there's an ASHRAE standard reference value there that you should do better than for your whole building of 0.3 CFM per square foot at 75. And both test samples with fasteners only performed significantly better than that whole building threshold. If you made your whole building out of just fastened CLTs with no other penetrations or things that buildings need, you do quite well. So 1 CFM for our 8x8 test wall for the CLT and half a CFM for the whole test wall for the MPP. More to come from that testing as we work through it. Last project, reuse potential of mass timber construction. Andre Barbosa is the lead PI on this. It's a much bigger, multifaceted project. Judith will be talking soon about LE reuse, which is part of this project. The actual reuse of the 10-story shake table, which you saw earlier, is part of this project. And this part I'm going to be discussing is using that 10-story shake table model and the information, the detail that's contained within there as a case study input in developing a tool for potential reuse in the future. And some of this is looking far into the future when there's more mass timber building stock being deconstructed and decommissioned, but also hoping that doing this in advance, there might be some lessons that can be applied to new mass timber construction that account for future reuse of that. So we're focusing just on the LCA world, on the part that can be reused beyond end of life. And this flow chart is actually incredibly big. That's shown in the lower right-hand corner, looking towards development of creating commodity products and reuse. We've heard about storage being an issue and having a project ready to go for that reused material when it's being deconstructed. This is looking at what reuse products might come out of that and what are the grading scenarios that would be required to make that happen. So we've come up with 7 different product scenarios, all the way from doing nothing, using it as is, to some what we think might be usable products that you can go to your nearest mass timber reuse supply store and pick up, to one that's pretty interesting that reuses existing CLT material or existing mass timber material as core, old replacement core for new feedstock on the outer lamella. I'll explain more in a minute. And combining that with some grading stages that these are big, broad categories on this slide, looking at whether that material needs to have visual characteristics and structural characteristics. in what combination. So low-grade use of reusing as is benefits for waste, but probably the lifespan is the new lifespan of that product is not going to be long. Beams and columns, maybe following the our dimensional lumber, there can be some standardized lengths and widths that can be cut and available. And if you know what's available, you can design your building around those elements. Same for blocks and logs. And we've come across some Finnish manufacturers, actually quite a few of them, that are producing CLT and GLT logs that with advanced machining even have double gasketed connections, and you can get a load of those and go build your cabin in the woods with CLT logs. So the other added benefit of smaller material, well, two things: smaller materials, they can be handled without special equipment for installation, and on the cutting from the existing panel side, you can get more of them out and inherently have less waste and more unitized products. On the panel side, standardizing wall heights, maybe there's 8 and 10 foot heights and 4 or 8 foot widths. And then this idea of using the existing panel as is, fastener holes and all, as core with new lamella on the outside that can have accomplish that visual grade and likely some structural characteristics as well, potentially producing larger reuse panels then can just be cut from existing material. If you can lay up with that core multiple smaller pieces with new and longer outside lamella. So getting too far into the weeds here, looking at fasteners and what ends up needing to be removed for, depending on which stage of grading you're looking at. The further you get to visual and structural, the more you remove. And the same example here shown in what's remaining after you go through that process. So the tool that we've created is a Revit to Rhino to Grasshopper to CSV export spreadsheet numerical results for waste and reuse efficiencies. But inputting that geometry, some intermediate stage where potentially this gets a rough cut basically, and it either goes to another facility, gets stored potentially, or it goes to cutting out of those standardized sizes after that point. This is a simple example of one of those stages in the tool where there's some circular or iterative processing optimization happening, looking at whether that first cut is longitudinal or transverse, and the implications that might have depending on your inputs and outputs. So in this case, the smallest block form that we're looking at, you have some minor but more reuse happening depending on which way that first cut. So there's a number of steps in the tool like that where it's optimizing based on required input and desired output. Much like a milling operation could prioritize market demand for what dimensional lumber is coming out, or optimize or optimize for waste and total board feet. So next steps for this one is the tool is done. We're validating now that tool logic and workflow, calculating the volumetric recovery and reuse efficiency for all of those many scenarios, comparing them and looking at embodied carbon and some logistics around transportation, storage, and fabrication. Thank you.